Welcome everyone to this explainer. Today, we're going to take the invisible, sometimes wild world of fluid dynamics and translate it into clear, totally usable tools for your engineering toolkit. Look, whether you're designing massive industrial pipelines or you're just trying to pass your unit operations exam, understanding exactly how fluids behave is an absolute must. So, let's get into it.
Here's our game plan for today. We'll start with the flow of fluids, move into decoding the Reynolds number, check out boundary layers and separation, solve some actual Reynolds number problems, and wrap up with manometers and pressure drop.
Section 1. The flow of fluids. Let's visualize the invisible.
To really grasp the math we'll be using later, we first have to picture how fluids actually move inside a pipe. You know, it's almost never just a solid block of liquid moving together perfectly. We essentially run into two fundamental types of flow: the smooth, distinct lines of laminar flow, and the completely chaotic, wavy lines of turbulent flow.
Think of it like this. Laminar flow is like a super well-managed highway. The fluid flows in parallel, straight lines with distinct streamlines, and nobody is changing lanes. This usually happens when the fluid is moving pretty slowly. But turbulent flow, that's basically a chaotic bumper car arena. The fluid moves erratically with cross currents and spinning eddies. There's complete mixing across the pipe, and this kicks in at much higher velocities.
Section 2. Decoding the Reynolds number. So, what actually decides if a flow is going to be an orderly highway or a totally chaotic arena? Enter the Reynolds number. We call it N sub R. This is a dimensionless ratio, meaning it has 0 units attached to it. It compares the fluid's forward-pushing momentum, its inertia, to its sticky internal friction, its viscous force. It's basically the ultimate predictor. It tells us exactly when that pushing force overcomes the friction, trying to keep everything in smooth layers.
It all boils down to this incredibly useful equation. Reynolds number equals D times U times rho, all divided by mu. Let's break that down real quick. D is the inside pipe diameter in meters. U is the average fluid velocity. Rho is the fluid's density. And mu is the fluid's viscosity, which is just a fancy way of saying its resistance to flow. Literally, if you have these 4 variables, you can predict any fluid's behavior.
And here is the real payoff. We calculate this because of these magic thresholds. If your math gives you a Reynolds number under 2100, your flow is purely laminar. But if that number jumps above 4000, you have definitively entered turbulent territory. And yeah, anything sitting between 2100 and 4000 is just a transition zone where things are kind of up in the air.
Section 3. Boundary layers and separation.
Fluids don't just flow in a vacuum, right? They interact with the stuff around them. As fluid moves through a pipe, friction against the solid wall creates what we call a boundary layer. In this layer, the outer fluid drastically slows down. But here's where it gets interesting. If the pipe suddenly gets wider, the fluid stream actually detaches or separates from the wall completely and shoots into the larger space like a concentrated jet.
Why do we care about this? Because that flow separation leaves an empty space between the expanding jet and the pipe wall, and nature hates a vacuum. That space instantly fills up with spinning fluid vortices, or eddies. These eddies cause a massive, completely irreversible conversion of your mechanical energy into heat. You are permanently draining pressure head from your system just because the pipe size changed too fast.
Okay, Section 4. Solving for Reynolds number.
Enough theory for a second. Let's apply this as a practical tool and tackle a classic problem you definitely see on a test. Here's example 7.9. We've got water flowing through a 25mm pipe at a speed of 2.041 meters per second. The density is 1,000 and the viscosity is 0.0008. The question is straightforward. What's our Reynolds number?
Let's walk through the steps. First things first, and this is an absolute lifesaver. Always check your units. We need our diameter in meters, so we have to convert 25 millimeters to 0.025 meters. Step 2. Set up our formula. NRE equals D times U times rho over mu. Step 3. Carefully plug in those values. So that's 0.025 times 2.041 times 1,000, all divided by 0.0008.
Crunch those numbers, and our calculation gives us a whopping 63,662.
Now, here's the so what of that result. Remember those magic thresholds we talked about? Because 63,662 is way past our 4,000 limit, we know with absolute certainty that this water flow is wildly turbulent. We've got cross currents and eddies mixing everything up inside that pipeline.
Finally, Section 5. Manometers and pressure drop.
So we know how fluid flows and how it loses energy,
But how do we physically measure the pressure driving it all? Enter the YouTube differential manometer. It's an awesome device that uses a heavy liquid, like mercury, sitting in a glass U-tube to push back against the flowing fluid. When you connect the two arms of the tube to different points in a pipe, you get this perfectly accurate visual display of the pressure difference. The heavier fluid gets pushed down on the high-pressure side and rises up on the low-pressure side.
To translate that physical height difference into an actual pressure drop, or delta P, we use this formula. Delta P equals H times the difference between rho m and rho times g. Let's unpack that. H is just the difference in height of the fluid inside the glass tube. Rho m is the density of that heavy manometer fluid, rho is the density of the lighter flowing fluid in the pipe, and g is our good old gravity at 9.81 meters per second squared.
Let's tackle one last problem to really lock down these skills. Example 7.2. We have a mercury manometer, and mercury has a crazy high density of 13,600 kilograms per cubic meter, reading a height difference of 200 millimeters for a flowing fluid of carbon tetrachloride, which has a density of 1,600. Our job is to calculate the pressure difference in newtons per square meter. Step 1, just like before, unit conversion. We take our height reading H and convert 200 millimeters to 0.2 meters. Step 2, set up the formula. Delta P equals our height, 0.2, times the difference in densities, which is 13,600 minus 1,600, times gravity, 9.81. Step 3, run that through your calculator. The math reveals a pressure drop of exactly 23,544 newtons per square meter. Think about that. Just by looking at a liquid level in a simple glass tube, we perfectly calculated the invisible mechanical forces acting deep inside our pipeline.
You know, as our source material notes, manometers are the simplest pressure measuring devices. It's pretty cool that sometimes the absolute oldest, simplest tools in engineering remain the most precise and reliable ways to visualize complex physics. Which brings us to the end of our explainer. But before we go, I want to leave you with a massive question to ponder. If every sudden pipe enlargement and every unoptimized fitting causes boundary layer separation and irreversible energy-draining eddies, just how much mechanical power are we silently losing beneath our feet in a whole city's underground water grid right this very second? It is literally an engineer's job to minimize that waste. Thanks for hanging out with me for this explainer, and keep questioning the systems around you.